In free-space optical communications, photodetectors are essential components that enable the reception of optical signals. Let's delve into how these devices function and their significance in FSO systems. At its core, a photodiode is a semiconductor device that converts light photons into electric current, as shown in the diagram. It consists of a p-n junction region where positive p-type and negative n-type semiconductor materials meet. When a photon with sufficient energy strikes the photodiode, it creates an electron-hole pair with the depletion region of the p-n junction. This generation of charge carriers results in a flow of current, known as photocurrent ID, which is proportional to the intensity of the incident light. Well, of course, we have to complete the circuit by biasing our photodetector circuit with some certain resistance RL and bias voltage VB. So the amount of photocurrent generated is directly proportional to the intensity of the incident light. This makes photodiodes highly sensitive to variations in light intensity, a crucial feature for detecting modulated optical signal in FSO. Photodiodes are typically operated under reverse bias, where voltage VB is applied in the opposite direction on the normal current flow. This increases the width of depletion region, enhancing the photodiode sensitivity and response time. The depletion region acts as a capacitor, and its capacitance affects the photodiode speeds. A wider depletion region reduces capacitance, leading to faster response time, which are essential for high-speed data transmission in FSO. The size of the depletion region also determines the photodiode's active area. A larger area can capture more photons, increasing the overall sensitivity, especially for weak signals. In FSO systems, photodetectors are crucial for converting the received optical signals into electrical signals that can be processed and decoded. By understanding their operating principles and key characteristics, engineers can select the most suitable photodetectors for specific FSO applications, ensuring optimal performance and reliability. In free-space optical communications, detecting faint optical signals and converting them into usable electrical signals is crucial. To achieve this, we rely on photodetectors, such as the one presented previously, coupled with specialized amplifier circuit known as transimpedance amplifier presented here. Well, transimpedance amplifier is an operational amplifier circuit designed to convert the small photodiode current into usable voltage signal output. The diagram here represents the basic transimpedance amplifier configuration. The photodiode is connected in photoconductive mode with reverse bias applied for faster response. The feedback resistor, RF, determines the gain of the amplifier, with Vout equals minus negative electric current produced by the photodiode times multiplied by the feedback resistor value. So key advantages is high sensitivity. Transimpedance amplifiers amplify even very small photocurrents, making them ideal for weak FSO signals. Wide bandwidth. They can preserve the high frequency components of the signal, crucial for high-speed data transmission. Low noise. Careful design can minimize noise contributions, ensuring a clean output signal. So let's also speak about a few most common types photodiode used in free-space optical communication systems. So at the heart of the circuit is the photodiode, which converts the incoming light photons into proportional electric current. So as you can see, here we have, for example, one of the most common photodiodes, which is called avalanche photodiode, offer internal gain for higher sensitivity, making them suitable for weak signals. Pin photodiodes are simpler and more cost-effective, suitable for moderate signal strengths. And CCSS, charge-coupled devices, and PMTs, photomultiplier tubes, used in specific applications. With CCDs known for imaging, and PMTs for extreme low light detection. In free space optical communications, the detection process is crucial for extracting information from the received optical signal. Let's explore the two primary detection methods, non-coherent and coherent detection. So first, non-coherent detection. In non-coherent detection, the receiver doesn't need to know the phase of the incoming optical field. The detector simply responds to the incident power of the optical field, effectively measuring its intensity. Well, advantages are lower complexity. Non-coherent receivers are simpler in design and implementation. Low cost. Due to their reduced complexity, non-coherent systems are typically more cost-effective. While on the other hand, coherent detection requires the receiver to measure both the amplitude and phase of the optical field. To achieve this, a local oscillator at the receiver generates a reference signal with a known frequency and phase. The receiver optical signal and the local oscillator signal are mixed together, allowing the receiver to extract both amplitude and phase information. Advantages: coherent detection offers improved sensitivity, allowing for longer communication distances and higher data rates. It can effectively suppress certain types of noise, leading to better signal quality. Well, non-coherent detection is simpler but offers lower performance, while coherent detection is more complex but provides superior sensitivity and noise rejection. Non-coherent systems are more cost-effective, making them suitable for short-range or lower data rate applications. Coherent systems are more expensive, but offer greater capabilities for demanding applications like long-haul or high-speed FSO links. By understanding the difference between these detection methods, engineers can choose the most appropriate approach for specific FSO system requirements, balancing complexity, cost, and performance considerations. Direct detection is a fundamental method of receiving signals in free space optical communication systems. As this diagram illustrates, it's a straightforward yet effective approach that underpins many practical applications. So let's see how it works. So the journey begins with an optical signal, typically a modulated laser, beam transmitted through FSO channel. The transmitter encodes information into the optical carrier, usually using intensity modulation techniques like on-off keying. The signal then traverses FSO channel, encountering various challenges like atmospheric turbulence, attenuation, and potential interference. Receiver at the receiving end, a photodetector captures the optical signal and converts it into electrical current. This photodetector directly responds to the intensity variation of the receiving field, of the received light, hence the term direct detection. Amplifier: the weak electric current from the photodetector is amplified to usable level. Post-detection processor: the amplified signal then undergoes post-detection processing. This involves filtering, demodulation, and error correction to recover the original transmitted information. Received information: finally, the processed signal yields the received information, completing the FSO communication links. So, key advantages are simplicity. Direct detection receivers are relatively simple design and implementation, making them cost-effective and reliable. Maturity: the technology is well established and widely used in various optical communication systems. It's compatible with common modulation schemes like OK, which are widely used in FSO. What are limitations? Direct detection is less sensitive to coherent detection, limiting its range performance in challenging conditions. Noise susceptibility: it's more susceptible to noise and interference, which can degrade signal quality. Let's analyze direct detection when coupled with on-off keying modulation technique. So let's break down the key components. So first of all, the process begins with a received signal, where a signal carries binary data, where the presence of light represents a 1 and the absence of light represents 0, as we saw previously. Afterwards, we have photodetector is the heart of receiver. It converts incoming optical signal photons into electrical voltage Vt. This conversion is directly proportional to the intensity of the received light. Afterwards, we have bit integrator. So the electrical signal Vt then enters the bit integrator. Its role is to accumulate the energy of the received signal over a specific time interval, known as the bit duration TB. This integration is represented by a mathematical simple integral in the image, which represents summation. So afterwards, we have a threshold test. The integrated voltage V from the bit integrator is compared to predetermined threshold Vt. This acts as a decision-making step. If V is greater than or equal to Vt, the receiver interprets the received bit as 1. If V is less than Vt, the receiver interprets the received bit as 0. The outcome of the threshold test is the coded bit, successfully retrieving the original binary information that we encoded onto optical signal at the transmitter. In essence, direct detection with OOK is a simple yet effective method of receiving binary data transmitted via light intensity modulation. Let's delve deeper into the process of direct detection coupled with pulse position modulation. It's another essential technique in free space optical communications. So PPM encodes information in the position of the light pulse within a symbol period, offering better power efficiency and noise resilience than on-off keying. So let's break down how the receiver decomposes incoming PPM signal. So the process begins as previously with the arrival of optical signal represented by the wave line at the receiver. The signal carries information encoded in position of the pulse within a symbol duration TB. Afterwards, we have photodetector, which is similar to direct detection with OOK. The photodetector converts the received optical signal into electrical voltage signal Vt proportional to the light intensity. Afterwards, we have integrators for 2 intervals. Unlike OOK, which have 1 integrator, PPM requires 2 integrators. Each integrator covers half symbol duration for TB of 2. So integrator 1 integrates the signal over first half of the symbol duration, producing voltage V1. Integrator 2 integrates the signal over the second half of the symbol duration, producing voltage V2. The receiver compares the integrated voltages V1 and V2. If V1 is greater than or equal to V2, the decoded bit is 1. If V1 is less than V2, the decoded bit is 0. So the output of this comparison is the coded bit, revealing the original information encoded in the pulse position. In essence, direct detection with PPM decodes the signal by determining which half of the symbol duration contains the pulse. The integrator with a higher voltage output indicates the pulse position and thus transmitted bit, while